This article is about life tables, survivorship, and age sex structure. Governments around the world keep records of human birth and death rates, not just for the overall population of a country, but also for specific groups within it, broken down by age, by sex. Often, this data is arranged in summary called life tables. Enterprising insurance companies make good use of these life tables, taking the probability of death at a given age and using it to calculate insurance rates at it. Statistically, guarantee a tidy profit. So what they're saying is that some insurance companies will take a look at your lifestyle and they're able to compute that into your risk of death. So then your insurance quotes or your life insurance or whatever insurance you get would be based off those calculations. So if you are a skydiver, you do that for a job, your risk of death or probability of death would be higher than someone, let's say, that is working from home. Okay? Ecologists often collect similar information for the species they study, but they don't do it to maximize their profits. They do it to gain knowledge and often to help protect species. Take, for example, ecologists concerned about the endangered red panda. They might follow a group of red pandas from birth to death. Each year, they would record how many pandas had survived and how many cubs had been born. From this data, they could better understand the life history or the typical survival and reproduction pattern of the red panda group. So they're able to tell by following that group how long a red panda typically lives, how long a male lives, how long a female lives, how many times a female will mate, how many cubs they will produce. So all that information goes into understanding the life expectancy of that red panda group and the survival of that red panda group. What's the use of a life history? In some cases, ecologists are just plain curious about how organisms live, reproduce, and die. But there is also a practical reason to collect life history data by combining birth and death rates with a snapshot of the current population, how many old and young organisms there are, and whether they are male or female. Ecologists can predict how a population is likely to grow or shrink in the future. This is particularly important in the case of endangered species, like the red pandas in our example. So for example, if you had a group of red pandas that were older, more elderly, you can expect them not to reproduce. They're kind of at their end of their life cycle. So therefore, in that certain community or habitat, the red panda population would decline or go down a little bit. Now, if you took a look at another habitat where you had red pandas that were young or middle-aged, you can expect that that population is going to mate and reproduce and create more red pandas, which is going to ultimately increase the population. So a life table, she just talked about, records matters of life and death for a population, literally. It summarizes the likelihood that an organism in a population will live, die, and or reproduce at different stages of their lives. Let's start simply by taking a look at the basic life table that shows survival rather than survival and reproduction. Specifically, we'll focus on the animal below. The Dall mountain sheep, a wild sheep of northwestern North America. For full disclosure, this data was collected in a pretty weird way. An ecologist named Olaus Mori hiked around Mount McKinley National Park in Alaska for several years in the 1930s and 1940s. Every time he came across the skull of a dead Dall mountain sheep, he used the size of its horn to estimate how old it must have been when it died. From the ages of the 608 skulls he discovered, he estimated the survival and death rates for the sheep across their lifespans. Below we have a table based on Mori's skull collection. To make it easier to read, the table is standardized to a population of 1,000 sheep. As we walk through the table, we can picture what will happen on average to those 1,000 sheep. Specifically, how many will survive or die in each age bracket? Let's walk together through the first row of the table. Here we see that 1,000 sheep are born, reach an age of 0. Of those sheep, 54 will die before they reach 0.5 years of age, or 6 months. That makes the death or mortality rate 54 out of 1,000, or 0.054, which is recorded in the far right column. So they're saying if 1,000 sheep were born, they were able to figure out that 54 of them would perish by reaching 6 months of age. So whether they got a disease and they died, or they hurt themselves, or they became a snack for another animal, that all goes into that. So the rate would be 54 died out of the 1,000 that were born. And then in your chart, you can see from the second column says, or the second row is from 6 months to 1 year. There would be the number dying in age would be 145. From 1 to 2 years old, 12 would die. From 2 to 3 years old, 13 would die. 3 to 4 years old, 12 would die. And all the way down, that shows you kind of how the number decreases over time in their age bracket. So by the time that the sheep are 12 and 13, or 13 and 14 years old, there's really only a few of them left, which also shows you their lifespan, that their lifespan is typically about 11 to 14 years old. By looking at the life table, we can see the sheep have the greatest risk of death. When the sheep have the greatest risk of death. One high-risk period is between 6 months and 1 year. This reflects that very young sheep are easy prey for predators and may die of exposure. Exposure meaning like to the elements where they're at. The other period where death is a high rate is late in life, starting around age 8. Here, the sheep are dying of old age. This is a relatively bare bones life table. It only shows survival rates, not reproduction rates. Many life tables show both survival and reproduction. If we added reproduction to this table, we would have another column listing in the average number of lambs produced per sheep in each age interval. Survival curves. For me, a life table isn't the easiest thing to read. In fact, I'd rather see all the survival data as a graph. That is, as one survivorship curve. A survivorship curve shows what fraction of a starting group is still alive at each successive age. For example, the survivorship curve for the Dal Mountain sheep is shown below. So as you guys can see on that graph, starting at the left-hand side where it has 0 and 0 to 0 to 0.5 with the age interval, you have the most sheep there. And then the graph goes down over time, and that decrease shows you how quickly the sheep are dying compared to their specific age. So you guys can see up at the top, from 6 months old to 2 years old, there's a huge drop off or decline. So that would tell scientists that that age for the sheep is kind of a critical age where they could easily face death, whether that being not able to defend themselves against larger animals, or they're more susceptible to getting sick or hurting themselves, and they're not able to be independent yet. And you can see that kind of same trend closer to the end of the sheep's life, or the 12 and 13 year marks, that you have that drastic decrease all of a sudden. And that shows that this shows scientists that sheep typically have the lifespan between 11 and 14 years old. And then in the middle, you guys can see how the curve is just kind of slowly going down. So it says down below, the graph makes it nice and clear to see that there's a small dip in sheep survival early on, but most of the sheep die relatively late in life. Different species have differently shaped survivorship curves. In general, we can divide survivorship curves into 3 types based on their shapes. Type 1. Humans and most primates have a type 1 survivorship curve. In a type 1 curve, organisms tend not to die when they are young or middle-aged, instead die when they become elderly. Species with type 1 curves usually have small numbers of offspring and provide lots of parental care to make sure those offspring survive. So we as humans, we are type 1, okay? We have a limited number of offspring that we produce at a certain amount of time. Okay, so typically women are having 1, maybe 2 children. Okay, and they're making sure those children are getting that extra care. And we also have the assistance of medical care to help us avoid any sickness or any problems we run into. So that is the type 1 curve. That means that we really, as humans, don't worry about death until we become elderly and hit that stage of our life. Next is type 2. Many bird species have a type 2 survivorship curve. In a type 2 curve, organisms die more or less equally at each age interval. Organisms with this type of survivorship curve may also have relatively few offspring and provide significant parental care. So that means that if you look at your chart, the bird's decrease of survival rate is going down in a way where they are dying more or less at each age interval. It's going down at a constant rate, where if you look at type 1, which is the blue line, we have a curve, a super slight curve, until we reach the end of our lives or we become elderly, and that curve really dips down. The birds which are in the red, that shows that their population of species is decreasing at a equal rate throughout their entire life. And then you have type 3. Trees, marine invertebrates, and most fish have type 3 survivorship curve. In a type 3 curve, very few organisms survive their younger years. However, the lucky ones that make it through youth are likely to have pretty long lives after that. Species with this type of curve usually have lots of offspring at once, such as a tree releasing thousands of seeds, but don't provide much care for their offspring. So that curve is shown in green, and a great example of that is something we talked about before, which we've talked about with sea turtles. Sea turtles will lay hundreds of eggs all at once, and then the mom, after laying the eggs, will go right back out to sea and just leave the eggs there. Now, out of those hundreds of sea turtles, perhaps only 10, 20, 30 are going to survive, which are quite a few. The rest of them are going to get picked off by animals looking for a delicious snack. But those who survive are going to live a really, really, really long time typically. Remember, sea turtles can live hundreds of years. The same thing with other marine animals, sharks and whales and fish. They can live a really, really long time. And the last thing we're going to talk about is age, sex, structure. How can we use birth and death rates from a life table to predict if a population will grow or shrink? To do this effectively, we need a snapshot of the population in its present state. For instance, suppose we have 2 populations of bears. One made up mostly of young, reproductive age female bears, and one made up of mostly of male bears past their reproductive years. Even if these populations are the same size and share a life table, have the same reproduction and survival rates at a given age, they're likely to follow different paths. The first population is likely to grow because it has many bears that are in prime position to produce baby bears or cubs. The second population is likely to shrink because it has many bears that are close to death and can no longer reproduce. So who's currently in a population makes a big difference when we are thinking about future population growth. Information about age, sex structure of a population is often shown as a population pyramid. The x-axis shows the percent of the population in each category, with males to the left and females to the right. The y-axis shows age groups from birth to old age. It is common to see pyramids used to represent human populations. In fact, there are specific shapes of pyramids that tend to be associated with growing, stable, and shrinking human populations, as shown below. So you have, in your age structure diagrams, you have the males are listed as blue, the females are in pink, and then they show the rapid growth, slow growth, stable growth, and shrinking growth. And you guys can see the differences in structure for each of those. If both male and female are reproducing and thriving at a similar rate, it's going to be this curved shape, okay? The slow growth is represented by a triangle, and the rapid growth is kind of an indented triangle. Countries with rapid population growth have a sharp pyramid shape. Their age structure diagrams, that is, they have a large fraction of younger people, many whom are of reproductive age or will soon be. This pattern often shows up for countries that are economically less developed, where lifespan is limited by access to medical care and other resources. So rapid growth would be in areas that are more poverty-stricken, where people don't have access to adequate food, housing, shelter, medical care. That is going to be or show their rapid growth. Areas with slow growth, including more economically developed countries like the United States, still have age-sex structures with a pyramid shape. However, the pyramid is not as sharp, meaning that there are fewer young and reproductive age people and more old people relative to rapidly growing countries. Other developed countries, such as Italy, have zero population growth. The age structure of these population has a dome or silo shape with an even greater percentage of middle-aged and old people than in slow-growing example. Finally, some developed countries actually have shrinking populations. This is the case for Japan. The population pyramid for these countries typically pinches inward towards its base, reflecting that young people are a small fraction of the population. The basic principles of these human examples hold true for many populations in nature. Large fractions of young and reproductive individuals mean a population is likely to grow. Large fractions of individuals past reproductive age mean a population is likely to shrink. So if you have a lot of young, healthy people, your reproductive rate is going to be a lot higher and grow a lot quicker. If you have a lot of middle-aged or older people in a country or in a community, your growth rate is going to be slow, or it's very much likely to shrink.